Good. Alrighty, so let's get started. Um, so our motivation was we wanted to get policy gradient, model-free RL to work for robots. But when we did policy gradient, we said that, hey, this thing is inefficient for two reasons. The first is because on policy, it's only using the latest batch of data. And the second is because it's high variance, right? So we said it's high variance because you're kind of like wiggling this rope, you're using a single sample estimate. It's really hard to tell which things matter, right? It's just really hard to tell if this thing was good or not because outcomes are tied with everything else in the future. So if you get really lucky, it gets weighted up. If you get really unlucky, it gets weighted down. And so it's high variance and it's on policy. And so our goal in off policy RL is to develop a low variance off policy RL algorithm that can bootstrap from prior data, right? So you don't want to just use, right now we're not saying prior data from an external source. I'm just saying all the iterates from iteration 0 of learning to iteration k, I want to use all of that data, right? Okay, so we said we can think of like policy gradient as a single sample estimator, which means that at some state, let's say, oh no, at some state st, right? Let's say this is st. We have a single trajectory, and we say we're just going to like upweight or downweight the actions by just the same trajectory, like the one trajectory that we had at that state, right? Because we're in a measure 0 continuous space, so you'll never ever end up at that same state ever again. And so you only have a single sample estimate, right? So what you really care about is something that looks a little more like this, right? You care about like you want to average how good the outcomes are for taking some action A at some state S. But really what you're doing in policy gradient is you're doing it for a single sample estimate. So when I say single sample estimate, I mean just for that trajectory. Right? And so the key idea in off policy RL, or the key idea we're going to use is to use the magic of function approximation, right? So I may never ever come back to this state, but I may come back to states that are nearby, right? So I will never get something that like in certain problems you can, right? Like in GRPO, you can teleport, but in most robotics problems, you can't teleport. And so I never may end up here, but I'm going to end up in three states that are relatively close to each other, right? And so if I train a function approximator, which means that I'm not going to just train something on like things from the same trajectory. I'm going to instead take all of this data, put it into a function approximator, let's call it Q for a second, right? It tells you how good is some action A at some state S, right? And then in place of our single sample estimate, let's just use QSA. Okay? So the important thing is that because I'm using function approximation, you can kind of think of it as it's sharing information between those trajectories, right? So the way function approximation works is that you start with the data set. In our case, it's those three trajectories. You use some like SGD procedure to give you some theta, right? Some parameters. And then those parameters, sorry, folks. Those parameters are what you're going to use to make predictions, right? So you're going to do Q theta of SA. But the important thing is like, it's almost like you're like averaging across multiple trajectories because they're all going into the same theta, right? So they're all affecting the same theta. So you're not just doing a single sample estimate. The parameters theta is what ties those trajectories together. And so the magic of function approximation is basically, even though I only had one trajectory from here, the nearby trajectories help lower the variance, right? But that kind of like makes one thing obvious, which is that it's relying on some representation of your neural net to tie those things together. It's like a little bit speculative, right? And so it's not always clear that this, and this share information right. And so what makes off policy RL with function approximation hard is it's like implicitly relying on the representation to share information, but like there's no guarantees. Right? And so don't think of this as something with lots of guarantees. It's still like very much understudied. Yeah.
Maybe you already mentioned some. Is how do you actually get the other like trajectories to them? You just run the policy.
Yeah, so imagine that you ran the policy a bunch of times to get all of those trajectories, right? And so let's call this state S1. Let's say you took action A1. Let's call the state S2. Took action A2. So this is S3, took action A3, right? And let's say the sum of rewards in the first trajectory, let's call it capital R1, capital R2, capital R3, right? So I'm going to construct a data set now, S3, A3, R3, S2, A2, R2, S1, A1, R1, right? And then I'm going to do regression. I'm going to treat these as the input. I'm going to treat these as the output. And you could do regression, and so they all go into the same parameters. But all of these came from running the policy, but you never revisited that same state. Cool. All right. So the primary object we're going to be using is this thing called a Q function, right? So a Q function is the expected sum of rewards starting at some state ST80, and then following the policy thereafter, after taking the first action as 80, right? So it's like I'm starting at ST. I'm going to take one action 80, which goes as input to the Q function. And thereafter, I'm going to follow the policy pi. Okay? And so whenever you say Q pi, that means you're going to take one action according to 80, which doesn't have to come from pi. It can come from anywhere. And thereafter, you're going to follow pi. And it's going to be super important that the first one is not from pi, because that's what's going to let you be off policy. Okay, so you can kind of think of the Q function as saying, if I had run the policy multiple times, I'm going to like sum up the rewards into the future. And if you want to have a if it's infinite horizon, you can have a discount here. Yeah. And so you're going to have a discount, and you're going to say it's going to be the expected sum of rewards into the future, sum up each trajectory, and then average it over all of the trajectories that you got, right? So this is the sum of rewards. This is the expectation. Okay, so a Q function is the expected sum of rewards in the future when you start from S, take action A, and follow the policy pi after that. And so a Q function is kind of the entity we want, because the intuitive way to think about a Q function is it's telling you how good is an action A when you take it at S if you had followed policy pi afterwards, right? So it's giving me how good A is at S. And if you have this, then you just increase the likelihood of good A's and decrease the likelihood of bad A's, right? So the nice thing about the Q function is when you define it this way, you just like sub it in for the policy gradient, right? So you say that normally this thing tells me how good some action A is at some state S, right? It's just like the single sample estimate. I'm just going to get rid of this guy. I'm just going to replace it by this guy. Yeah. And so the way we're going to connect this to policy gradient is saying, if we can estimate this Q function a different way, we're going to estimate it in off policy low variance way, then we can just sub in the Q function in place of the sum of rewards. That's going to be lower variance. It's going to get rid of some of our problems from earlier. Cool. So, and we're going to represent our Q function with the neural net, right? As one does. In our case, we can think of a Q function as something that takes an S and A and outputs a scalar. Yeah. And in discrete cases, you often have something that takes an S and outputs like a vector of dimension A, but it's like a scalar for every single action, right? So in continuous spaces, you often will feed in actions as input. In discrete spaces, you'll produce like an action dimensional output, or just a bunch of scalars. Okay, nice. So we talked about this last time, but our first attempt at getting a Q function is the simplest one, right? Remind me of your name.
Hisham.
Sham?
Hisham.
Hisham. As Hisham and me were just talking about, right? Like you basically say, I'm going to take a bunch of samples, right? For each of the samples, S and A, I'm going to compute the sum of rewards in the future, and I'm just going to do regression, right? I'm just going to say, I'm going to say Q of SA minus like the sum of rewards. I like minimize this over N trajectories, right? So I just like run my policy in the world. I minimize this over some bunch of trajectories, and I can get a Q function, right? This is the correct definition of a Q function. So this thing will give me QSA, and then I can like stick that thing in place of the sum of rewards, and it's still going to be better than the sum of rewards, right? Because it's not single sample estimate. So I just do a regression problem. So normally what policy gradient does is it runs things. It computes the sum of rewards. It computes the gradient. It steps the policy, right? You'll just add one extra step, which is a regression to get a Q. You're going to stick the Q in, and you're good, right? So what's the challenge with this? Like, why don't we do this all the time? Yeah. Yeah, you have to get complete trajectories, and you have to do it from your current policy again, right? So it's still on policy, and it's still high variance because all the trajectories are still tied together, right? It's lower variance than the previous thing, but we can be even lower variance. right? And so it's unbiased, but it's going to be high variance and it has to be on policy, right? So we're not able to use, because QPy is under my current policy, I can't use like arbitrary old data. Right? And so this is not going to be our answer, but it's one step closer than policy gradient. Right? So policy gradient was, you're going to have sum of R, right? And what we did is we went from the sum of R to a Q function, right? So the Q function is kind of like an expected sum of R, which shares things across many trajectories. Good. Okay, so that's attempt one. Attempt one is a failure. So we're going to say that we want to do better. We want to reduce variance even further, and we want to be off policy, right? And so we're going to use some special structure in our Q function or in our value function. So someone remind me what that special structure was. We're an MDP, right? So is there more structure we can use in our value function to lower the variance? No? Yeah.
The value function of instead is the expectation of only of reward as the value function of the.
That's right. So we're going to have like a recursive structure in our value function. That's going to be what we use to lower the variance further. Okay, so let's try to rederive this, right? So we're going to say, remember our policy gradient. We're going to replace the sum of rewards by the Q function, right? And we're going to say a Q function, remember, is the sum of rewards in the future. When you start at some state S, you take an action A and follow the policy phi thereafter, right? And so that's our Q function. That is our policy gradient. We're going to now just find a better way to estimate the Q function. Yeah. Okay, so the first thing we're going to do is we're going to introduce a value function, right? A value function is just, there's no like separate action that you take, right? It's saying that if I ran the policy from state S, start at state S, I just ran the policy, what is the average reward? That's it. It's simple, right? You're just saying, start at state S, run the policy, average a bunch of stuff. So that's the definition of a value function. Can you remind me, how do you connect the value function and the Q function? Q function's up there, value function's here. How do you connect them?
The values of that for all the.
That's right. The value is the expected Q function under the policy, right? So you can kind of think of this as the Q function takes one action A and then follows the policy. The value function always takes pi, actions from pi. So if I take the Q function and I just sample the first action also from pi, then I get the value function, right? And so you can say that the expected Q function with the first action also sampled from pi is the value function, right? So that's how you go from Q to value. And the next slide will go from value to Q, right? But Q and value are super connected. Okay, so we define policy gradient, Q function, a value function, right? Now, what we're going to do with the value function is we're going to try and define a recursion, right? So remember, the value function is the sum of rewards into the future when you start at some state S. First thing we're going to do is we're going to separate out the first reward from every reward in the future, right? So we're going to say that this sum is basically R of STAT plus a sum from T plus 1 to capital T of R whatever, SKAK, right? This basically you're separating out the first one from everything else. So I haven't done any magic yet. I've just separated out the first from everything else. And the the next somewhat convoluted objective is basically just it's using this law of iterative expectation. So whenever you have an expectation over two variables, right? So let's say you had expectation over two variables. Something like that, yeah. Right? Something like that. You can write it as expectation X, expectation Y given X of F. Right? So the law of iterative expectations lets you separate out an expectation, two separate expectations. Right? And so essentially ignore all the like the fanciness here, but all it's really saying is that I can separate out this objective into the sum of the first reward plus the expectation of all the future rewards, right? And so I'm saying I initially have a sum, expected sum over everything. I just separate out the first reward plus the expectation of all the future rewards. Yeah. And if you look at this expression, I made a little typo here, but basically take this thing out here. But if you just look at this second sum, right? The sum of rewards in the future, that just looks like a value function starting at t plus 1, right? And so you can think of this as like, it's the expectation of the reward plus the value function in the future, right? So the nice recursive structure, which is called the Bellman equation, tells you that the value function at some state s is the reward function plus the value function at the next state, right? And so this kind of intuitively makes sense because imagine you can think of a Markov chain like this, right? If I say I had the value function from here on, I'm going to say the value here is equal to this thing plus the value here, right? And the value here is equal to this thing plus the value here. So you can kind of think of this Bellman equation as like a backward recursion starting from the end, and you're just like summing up rewards going backwards. Right, but the nice thing is you can do function approximation on like individual pieces, right? So if you think of this as like it's more useful to think of this as kind of like a tree, right? And so what's happening here is that I'm like averaging all of these. I don't have to take a single sample estimate through the tree. I'm like averaging all of these and I'm kind of storing it into my Q function, right? Or into my value function. And then over here, I can just take the average value which is stored in the Q function and back that up and back that, right? So you can kind of think of it as, let's see. Let's draw a tree. Oh man, I haven't drawn a tree in a long time. So if you think of this kind of tree, right? It's like averaging this value, storing it here, right? Averaging this value, storing it here. And then averaging these values, storing it here. And so your like dynamic programming is going up the tree, right? And so value functions obey this Bellman update, but the Bellman update just connects B at some state to B at the next. And remember here, there's a few things that are important. Is the things that are in your expectation, right? So you're sampling actions from your current policy. You're sampling the next state under your dynamics. And that's how you compute your Bellman update, right? So the Bellman update is not just like, it is like an expectation over the next thing, right? And so it's not just a single sample estimate. You're saying it's an expectation. So in some ways, you can think of it as from this state, I could have multiple possible outcomes, right? So I could have multiple different actions, and for each different action, I could have multiple different states it transitions to. So these are each of the actions that I could sample. And for each of these, I could also have multiple future states, right? And so what this thing is doing is for each of them, it's computing for each action and next state sample, it's computing the R plus V and then averaging all of those, right? So it's giving me the average value of the loop node of the string. Cool. Makes sense overall? Everyone kind of with me? Any questions? If you don't ask me now, it's going to be waste of 70 minutes of your life. So ask me. We're good? Cool. Okay, so what we figured out is that value functions are recursive, right? So value functions are recursive, so you can write v pi as r plus next v. And so, but our policy gain update was in Q, right? And so we showed how to go from Q to V, but here we need to go from V to Q, right? So we had a way to get V's through this recursion. Now we need to go from V to Q so I can stick it into policy gradient. And so the simple thing we're going to look at is what's the definition of a Q function? The definition of a Q function says you're going to start at S, take action A, and then sample the next state from the dynamics and sum up the rewards in the future, right? And so you can also decompose the Q function into what you call a one-step look ahead or one-step backup of the V. So you can write that the Q function, Q pi TSA, is equal to R plus, one sec. You can say that's equal to R plus V at the next state, right? So if I ever have a Q function and I have a value function at the next state, right? You can kind of think of it as a Q function is saying I'm at this state S, right? I'm going to take some action A. That action A is going to transition me to some S prime. Actually, it'll transition me to some distribution over future S primes, right? What I'm going to do is I'm going to take my reward at that state. I'm going to take all my values at different S primes. I'm going to average all of them. And that's going to give me my Q function, right? And so you can say, if you think of it from this tree structure, This is my current state. This is the action that I'm going to take in QSA, right? And from here, I could have like a stochastic transition model. So I could say I could transition to this state with some probability, this state with some probability, and this state with some probability, right? And for each of them, I can compute what V of S prime is going to be, right? It's the value of the future state I would have gotten. And then I say that I'm going to take R plus V S prime, which is going to give me the value of like each of these branches of the tree, right? If I take each of these branches of the tree, it's R plus V S prime. Each branch reaches a different S prime, and I average all of those to get the Q, right? So if I'm going to say, it's kind of saying, if I took action A at state S, I stochastically transition to different S primes according to the dynamics. I average my current reward plus the value of those future states I could have reached, right? And that gives me my future Q function, or gives me my Q function when I take A and then follow policy pi. Okay? So you can always go from Q to V by taking the average Q function that gives me V. You can always go from V to Q by doing a one-step look ahead, right? So it's kind of like saying, if I want to know how good an action is now, I'm going to see which states does my action reach, and then see how good those states are. Cool. So I'm going to have a V function. I'm going to have a Q function. Q function is just one step look ahead, and then I like stick it back into my policy gradient. Okay? So I'm doing policy gradient as usual, as we did all of last lecture. But now, instead of doing sum of R along a single trajectory, we're going to try and like substitute it with this like R plus future V, right? So here's one way of thinking about it, which is imagine you had a trajectory, right? Earlier, what we did is at some state S, we were going to like sum up the whole trajectory. Now what we're going to do is at this state S, I'm going to look at S, A, S prime, like what did it transition to, right? And then I'm going to like replace the sum of R with the current reward plus the future reward. And that is going to be my approximate Q function, right? And so instead of sum of reward, like we did earlier, we're going to do R plus VS prime. Yeah? Everyone with me so far? So what that means for policy gradient is we're going to say grad log phi of A given S times R plus gamma V S prime. Yeah. And now when we have a baseline, you can subtract a value function. So you have R plus gamma Vs prime minus Vs. Right? So we're just going to have the same expression for policy gradient. We're just going to replace the sum of rewards with the Q function. The Q function is R plus gamma V. We subtract the baseline to get minus Vs. Right? So let's try to put those pieces together, right? So for policy gradient, what we're going to do is we're going to try and first get the V, and we can use this recursion to get a V. Once we get a V, we're going to use, and this is through the Bellman update, right? We're just going to use this recursion to get a V. Once you get a V, you're going to do one step back up to get a Q. Once you get a Q, you replace the sum of rewards in the policy gradient with the Q. Okay. Cool. So the way we're going to do this is we're going to use this like this update, which is saying I'm going to construct targets, which is R plus future V. And I'm going to try and match V of S with R plus V of future S, right? So I'm going to try and essentially you can kind of think of this objective as making the left and the right-hand side of this the same. Yeah. So this side is V of S. This side is R plus V of future S, right? So you're trying to make this and this the same. Yeah. So the first thing we're going to do is we're going to try and get the value function, which at convergence is going to satisfy this Bellman equation, which means that V of S is equal to R plus V of future S. And so this is going to give me my value function. And once I have my value function, I stick it back into the policy gradient update. And I stick it back into the policy gradient update by saying, well, Q is now R plus V of S prime. And I subtract a baseline, which is minus V of S. And so that gives me this update over here. So I start by solving for V, which satisfies the Bellman equation. And then I replace Q by R plus future V, and I subtract V of S. Yes.
So for the minimization equation, the theta be the one from the neural net and the B in the yi, the one we get from our the plus is
So in this case, both the left and the right-hand side actually have the same v. It's just that there's a bit of nuance to this because what you could do, right? What you could do is you could think of this as saying you're going to have like v phi s minus r plus v phi s prime, the whole square, and then minimize this with respect to phi on both sides, right? So on this side and this side, we have v phi both sides. The problem is that like your target and your thing are both changing at the same time. And so the stabilized thing, there's like a deeper reason for this, which we'll get to later in the lecture, but the stabilizer, basically, you kind of think of this as you're removing the gradient to the right-hand side. And then every so often you like flip it. Just like you're kind of having a stationary target, which is r plus v, and then you're not passing the gradient to the right-hand side. You're trying to hit that target, and then after you hit it enough, you like switch the targets. And so you can kind of think of it as it's a way to avoid instability by passing grades to the left and the right-hand side of that equality. Yeah, good catch. Yeah. Okay, so remind me, Fernie. Akash was just saying, you can kind of, this is not a different value, it's the same value, but you're kind of gonna have like a stop gradient here. Right, so the way you're going to implement this in practice is you'd have r plus v, you're going to stop grades, you're not going to have grades to the right-hand side, you're only going to pass grades to this, and then every so often you're going to swap on. So we'll talk about this idea of a target network in a second, but think of it as a way to do stability for now. Okay, some questions, sir? No. Cool. So you can kind of think of this as like a better estimate of like closer to this non-single sample estimate, because what you're doing here is like this V is the one that's doing this like bundling, right? So this V is the one that's doing this bundling. V is the function approximator. V is the thing that is sharing things across multiple states, right? And so we didn't want earlier what we were doing is we were just doing R plus some of R's in the same trajectory. Now what we're doing is we're bundling things across multiple states through this V. Cool. All right, so that's our second attempt at doing off-policy RL. Yes? No, it's a function approximator. So it's a neural net that takes in S. So it's like shared parameter. You are like retraining V at every iteration. So like in practice, what you do is you just warm start V from the previous steps. So you just like keep fine tuning it. Basically, remember this V is specific to a particular policy, right? So it's kind of like this is not. Sorry, I don't know what happened there. Okay, so this V is for a particular policy, right? And so it's not like as soon as the policy changes, you need to re-estimate V, right? So you can kind of think of this as we did a bunch of stuff. So like the V is going to be represented by some neural net. The neural net is going to take an S. It's going to give you a scalar. Yeah. And so I'm going to estimate it for some pi. I'm then going to make an update on the pi and then I have to re-estimate V. Right. And so you're going to, yeah, but it's still on policy. Yeah, exactly. That's the problem with it. But the good part is what you typically will do is you'll warm start the parameters from the previous value. So the value doesn't change that much across iterations. Cool. Okay, so we're gonna mind me for you as you were saying, we're gonna like essentially iterate between these procedures of fitting a value function, computing the policy gains, fitting the value functions, fitting V phi. Then you're going to update your policy. But remember, with an updated policy, you have to refit the value function, right? So you're going to fit the value function, compute the policy again, update your policy, collect more data on policy, and then you're going to go back and you repeat, right? So in terms of like where this is good is that it's lowering variance, right? It's, as we drew earlier, a single sample estimate would be, at this stage, you only compute this. Here, what's happening is you're doing something that looks a little more like this, right? So you're lowering variance, but as we just got to, it is still on policy. I still have to collect data every single time. right? I'm only using my latest data. Like if you remember the V equation on the top right? This is like S prime has to be drawn from my current policy pi. It can't be drawn from some other random stuff, right? It has to be drawn from my current policy pi. And so if I really want to be off policy, what I want to do is be able to compute this thing, but for some other policy data coming from some other policy pi beta, right? So the whole idea of being off policy is that I want to be able to compute that alpha. Still want to retain the variance reduction, but I want to do it from different data. Okay. So so what we've done is we've said, okay, there's two issues with policy again, variance and on policy. We've dealt with some variance problems, but we're still on policy, right? And so the next thing we're going to do is we're going to try and deal with this on policy-ness. Cool. One thing that I've been generally a little sloppy with throughout this class is like finite horizon and infinite horizon and so on. So this is a slide for reference. If you're finite horizon, you have to have like time index value functions, time index policies, time index Q functions, because what you would do with 5 steps left and what you do with 1 step left is different, right? And so whenever you like, if you want to be pretty precise with it, like make sure to time index everything, right? And so the Bellman equation, remember, is going to be from V pi sub t to V pi sub t plus 1, because the time index matters. And so you're saying on the left-hand side, I've taken t steps, on the right-hand side, I've taken t plus 1 steps. And so if you ever want to like do finite horizon, make sure time index everything. Yeah. Like imagine that you wanted to like get somewhere and stay there. Right. So it's like I wanted to stabilize a chemical plant around some like stable point or something. Or I want to stabilize a plane around some stable point forever. And so in those cases, it's not that what like the difference with the finite horizon thing is that it's like if I know that I have like 1 step left, I might do something super greedy. Whereas like if I have infinite steps left, then I have to do the thing that'll be good in an asymptote. Right? And so in practice, in robotics, often you use like infinite horizon because you like want to pick something up and keep it held. Whereas like if it's finite horizon, I'm like, okay, I'll be fine and then I'll drop it. And so you kind of want to avoid that behavior. Okay, and if you're being infinite horizon, then you don't have to be time index. It's a stationary value function, stationary Q function, stationary policy, but you have to be discounted, right? Doesn't make sense to be infinite horizon and not discount because it like will blow up to infinity. Cool. So if you ever feel confused about those things, just go back to the slide as reference. Okay, so we found that we have something that's lower variance, but it's still on policy. So the next thing we're going to try and do is we're going to try and do something off policy. Right? And so the basic structure of how we're going to be off policy is we're going to take our Q function, which is the sum of rewards in the future, starting from S and taking action A. And we're going to do recursion directly on the Q function, not on the value function. Right? And we're going to show that if we did recursion on the Q function, it's going to allow you to be off policy. Okay, so a Q function is the first reward, STAT, plus an expectation in the future under policy pi of your future rewards, right? But it's important that you are saying that like you have your first reward, and then you sample ST plus 1, I guess. You sample ST plus 1 from the dynamics of your system, right? So you say ST plus 1 comes from P of ST plus 1 given ST and AT, right? And the future actions, all the actions in the future are sampled from, not from the A that you specified, but from the policy, right? So AT plus 1 is sampled from your policy. Yeah. So this expectation under pi, but the first action is going to be sampled from pi at ST plus 1. And then I'm going to like just follow the policy pi from there on. So, okay, so now you're going to help me work this out, right? So if I like look at the right-hand side, and can I convert into some sort of a Q function? Like what kind of a how do I make this a recursion in Q? Like, what does the right-hand side look like? Any thoughts? Eric, what do you think? The right-hand side. I want to convert this equation into recursion Q. We know the definition of Q, and we've separated out the first term from all the other terms. So, like, how do I write this recursion in terms? Right. So, your Q function, the expectations are super important. Don't ignore them. Right? So, your Q function at time ST80 is equal to your current reward plus the expected Q function in the future, right? But the expectation is under ST plus 1 from your dynamics and under AT plus 1 from your policy, right? And so here the important thing is that the next state that you're getting to is coming from the dynamics. But remember, the thing you're feeding into the dynamics is action AT, and AT can come from anywhere. AT doesn't have to come from my policy. Right? So the nice thing here is that this AT can come from anywhere. But the thing on the right-hand side, this AT plus 1 has to come from my policy, right? So the important thing here is AT, like I'm trying to evaluate some policy pi. I'm trying to get a Q function for some policy pi. The action on the left-hand side doesn't have to come from pi. It can come from anything, right? The action on the right-hand side has to come from pi, right? And so that's what lets you be off policy, which is, you can kind of think of it as like you're taking one step and then acting according to pi, right? And so this one step can be from anything, right? As long as you're querying the next steps from pi, your one step can be from anything. And so what that allows you to do, and if you like take this one step and you just recurse it, right? You can say, here, the one step can be from anything, and then you can think of the two steps as being from anything, and then you can think of the three steps as being from anything. And so what that allows you to do is to like train a Q function from data that is not from pi, right? And so the cool part about this recursion here is that you can kind of think of it as dynamic programming. Again, you started from the back and you're propagating Q. But the nice thing here is that you can propagate it under data SAS prime that is sampled from some pi beta, which is not equal to pi. Right? And so the reason it's off policy is, remember, what you do have to do is you have to query the Q function on the right-hand side with actions from pi. So you need pi, but the first action doesn't have to come from pi. Yeah. And so you can kind of think of this as like you're going one step off and then following policy pi. And then once you go one step off from that state, you can think of going one step off again. And from two states, you can go one step off. Right? That gives you like the ability to take off policy data and get a Q function from off policy data. Yeah.
How important is it that like pi beta in this case is like a good policy versus like
It's a good question. So the question is, how important is it that your pi beta is a good policy rather than an arbitrary policy? It doesn't need to be good, but what it needs to have is coverage over relevant actions, right? So you can think of it this way, which is that, like, imagine that I was at S, this was S prime, right? And imagine that pi beta at S prime mostly samples stuff here, right? This is from what came from your data set, pi beta. Right? But what pi samples is like this guy, right? And so now I'm gonna like, this is what the data set was, this is what the Q function was trained on. But now I'm going to query the Q function with this A, which is like way out of distribution. Right? And so where this is going to struggle is if there's not coverage between your policy and your pi beta, but pi beta can be bad. So like what would be fine is, let's get rid of this guy. And let's say we had like that, right? And so let's say pi beta was actually pretty bad in that it had like lots of bad stuff too, but had coverage over some of the good stuff, then I think you'd be okay, right? And so the main thing is like this thing, like the Q function on the left-hand side is trained on some S and A, right? So you can think of the training distribution for the Q function as S prime coming from some pi beta, yeah? And then on the right-hand side, I'm querying the Q function under pi theta, right? The thing I'm trying to evaluate. And if this thing and this thing don't have overlapping coverage, then you run into trouble. Okay, cool. So the nice thing about this recursion is that here A doesn't have to be from pi theta, but here A is squared, AT plus 1 is squared from pi theta, right? And so you can be off policy. Yeah.
Kind of a follow-up, but I guess then you calculate that to say that if there's some like chain of specific actions that would yield a high reward, like your off policy approach would never actually find it if your data policy that you're sampling from never like goes through there, like never has the setting.
That's a great point. So there's two parts to it. One of them is action coverage, and the other one is state coverage, right? And so it's kind of like, imagine that you can think of it as like, if I ran the true policy pi theta in the world, let's say it like took this path and it reached great success, right? But imagine that, how do I color this differently? Okay, never mind. Imagine that my pi beta like had coverage on this stuff, right? But not on the like optimal path. Then like what I'll do is I'll propagate value backwards from here if pi theta had been in those states, but I'm never going to propagate value backwards from here because it was never the training data, right? So if your training data doesn't have, it's not like a silver bullet. If your training data doesn't have coverage over that star, it'll never propagate backwards. So the important thing is like within the coverage of your data, you don't have to act in the same way. Like the thing that collected your data and the thing that you're propagating backwards don't have to be the same, but the coverage needs to be overlapped. Okay. Yes. Yes.
Between like training the value function
Yeah.
and now training the Q.
Yeah. So here's the difference, right? So your value function, v pi s, right, was equal to an expectation of r plus v pi s prime. Yeah. But remember here that like s prime came from the dynamics, right? And the action came from your policy, right? So remember that this thing, the right-hand side requires data to come from exactly the same policy, like because you're sampling actions according to the same policy, whereas in this other case, it's coming from a different policy. Yeah.
So would you want to like have your pi data maybe separate uniformly so that you can chart the then maybe that makes it harder back for you?
I think the tricky part about sampling uniformly is that under a finite sample budget, you're wasting samples where it doesn't matter. And so you don't want to sample uniformly, but you often want to sample with coverage over the optimal policy plus minus some. So like typically you'd like, if this is your optimal policy, you like want to have like something of that nature.
Right. Obviously,
Yeah, it's a little vibes based. That's why you have exploration trying to give you coverage. So often like the purpose of exploration and maximum entropy and these kinds of things is to broaden the set of coverage so that you can cover the optimal policy. Right? So yeah, you don't know beforehand. So in that case, the best you can do is try to cover the optimal. Okay. Okay, good. All right, so this is still a recursion. Let's try to formulate it into an objective. But the nice thing is that it's off policy. The left-hand side can come from pi beta. The right-hand side can come from pi theta. They don't have to be the same. Right? So when we try to formulate it into an objective, you want to take this Bellman equation. You want to make it into an objective, right? Something that you can do gradient descent on, right? Something you want to like use to update the parameters of your neural net, right? So we're going to say that Q is going to be a neural net. We want to convert this into an objective to train that neural net. So how are we going to do it? Well, we're going to take the left-hand side, which is Q pi STAT with some function approximator. Let's say the parameters are phi, right? So we're going to say on the left-hand side, you have Q pi sub phi STAT. On the right-hand side, you have the target, right? So if you remember, like this thing is often called the target, right? That is the thing you're trying, that's your Q function, this is the target. And so what you're saying here is that you want to make QSA equal to the target. Okay? The target is like a one-step look ahead. And so QSA is equal to R plus Q in the future, right? But the important thing is that this is Q at some state ST plus 1, which is coming from the dynamics, and future actions that are sampled from pi theta, right? And so you can kind of think of this as an objective that looks like this. So you want to make the left-hand side close to the right-hand side. And you want to do it under S, A, S prime, sample from some data set D, right? And let's say data set D came from some pi beta, which you often call your behavior policy. Like the whole point here is that pi beta and pi theta don't need to be the same, right? And so I've converted this into an objective to get Q. You can think of it as like Q needs to match R plus future Q, right? Future Q is queried at next state S prime, which is coming from the data, but with action A prime, which is coming from the policy, right? And so you can kind of think of this as like graphically, this is SA, this is S prime. That's all from the data, right? All of this came from the data by beta, yeah? And what I'm trying to, what the behavior policy would do is, let's say this, but what I'm going to try and back up is this, right? So this is the action that is coming from pi theta. This is the action coming from the behavior policy. So what the Q function is trying to do is it's trying to propagate this thing backwards, right? So it's trying to propagate the thing that came from pi theta backwards, not the thing that came from pi beta. Right? Pi beta is your data. You're not trying to propagate the data. You're trying to propagate the thing that your policy would have done at the next state. Okay, so the way that you will implement this in code is that you would have you'd have like some data set, right? Let's say your data set was S, A, S prime R, yeah? For all the S, A, S prime Rs, left-hand side is going to be QSA. Right-hand side is going to be R plus Q. You're going to stick in S prime, and then you're going to sample an action A prime from your policy phi at S prime, and then you're going to stick in this action into here. That's going to be your target, right? And then you're going to solve it with gradient descent. Right? So you're going to try to solve for the parameters of Q phi with gradient descent. Cool. So the way you'd like construct this into an objective is you sample S, A, S prime from your data set. You sample AT plus 1 or ST, AT, ST plus 1 from your data set. Sample AT plus 1 from your policy. You construct this into an objective, and then you just do gradient descent on the parameters phi. And you can represent the Q function with the neural net, and you just do like stochastic gradient descent, mini batch. You can do it with mini batches, right? The nice thing about this is it doesn't have to be from the same policy. So you can just like take a big data set, you can just sample mini batches and do mini batch gradient descent of this. And once you have the Q function, you can then do like gradient. You can do policy gradient with it. We'll get back to that in a sec. But one thing to note here, which I'm like sweeping under the rug, is that I've like made this like a phi hat. I made this a phi, right? That's not like a typo. The left-hand side and the right-hand side are not the same. So like I was just telling you right here, this thing, you kind of put a stop gradient around it. So you don't pass the gradients to the left and the right-hand side because you like don't want instability in your optimization. So you don't want the left and the right-hand side to both be changing all the time. So it's kind of like trying to hit a target and the target is always changing. And so when you like pass gradients to both the left and the right-hand side, it's called Bellman residual minimization, and it doesn't work very well. And so often what people will do is they like stop gradient on this side, and every so often you like flip the right-hand side. And as a result of doing this somewhat sketchy procedure, this is often called a target network. This is called a target network. And this sketchy procedure changes this thing from gradient descent to fixed point iteration. So it's not gradient descent. It looks like gradient descent, but it's not because your objective is constantly changing. It's not like doing gradients on a consistent objective. It's like your objective is constantly changing. And so that's what makes the dynamics of like off policy RL kind of hard to understand because it's not gradient descent. Because you're not passing gradients through both sides of the objective. Question? No, you're just raising. Okay. Good. Okay. So we'll cover this in a little more detail in the future. But generally, if you want to implement off policy RL, what you're going to do in your homework is you're going to take in any tuple of SA S prime R. You're going to construct the left-hand side from S and A, right-hand side from S prime, and then sample an A prime from your policy. And then you will just do gradient descent, right? But stop gradient on the right-hand side. Good. That's off policy RL. Now we have things that are off policy because this data can come from anything, including all the past iterates of training, right? And it's low variance because you're doing dynamic programming, right? So you have like both the desiderata you care about, you're trying to like minimize variance and you're trying to be off faults. Okay, so let's put all the pieces back together, right? So now we have a way to train our Q function, right? Now we want to go back and improve our policy. We don't care about Q functions, we only care about policy. And so the last bit is to say, once I have a Q function, I want to like improve my policy with my Q function, right? And so what we want to do is we want to optimize an objective that looks like this. And what this objective says is that from states from my data set, if I sample actions from my policy, I want them to have as high Q function as possible, right? So it's kind of like saying at this state, I want to sample actions from my policy such that my Q function is as high as possible, right? So if you remember like the previous RL objective, I'm trying to sample trajectories from some P theta tau such that R tau is as high as possible. It's like the same objective, right? You're trying to say, if I have a Q function that tells me that A is good at S, how good is A at S? I'm trying to find a policy that puts all the sampling weight on good A's, right? The more I have good A's, the higher the Q function will be. And so this part is called policy improvement. So you got your Q function, which is called policy evaluation. And you're trying to improve your policy now, which is called policy improvement, right? So you're trying to find a policy by theta, which maximizes my Q function. Right? So you can kind of think of it as like, the Q function says, if I took action A and then followed policy pi thereafter, what would happen? And this procedure says, well, what if I found the best possible A and I like change my policy to increase that likelihood? Okay, so I want to optimize this objective. How do I optimize it? Like, remember, it's like not supervised learning because the expectation has a pi theta in it.
Why is pi theta a function?
A is a function of pi theta.
Like A is drawn.
A is drawn from pi theta, yeah.
A is also in the parentheses.
So it's kind of like, this is going to be like an integral of P, like S drawn from some data set. Let's call it with some likelihood PD. And it's going to be like, pi theta of A given S of Q of SA. TSD. Right? So it's kind of like saying, to compute this expectation, you sample states from your data set, you sample actions from your policy, you sample S and A, and then you stick in S and A into your Q function. Right? So it's kind of like if I'm doing an expectation over X comma Y of f of xy, right? You can think of that as double integral px, py, fxy, dx, dy. In this case, x is states, y is actions. Right? So you can kind of think of it as you're sampling states, you're sampling actions, you're sticking them into the Q function. That's it. And you're sampling, like I think for now, just ignore this thing for a second. Right? Just think of this as you're sampling states, you're sampling actions, then you have something that scores those actions, and you're just trying to find you're going to put the likelihood where the score is the highest. That's it. So what it looks like is one-step policy gradient, right? So you can think of this as like exactly the same as one-step policy gradient. If you remember how policy gradient worked, if we had something like this, right? Remember, this is the same thing we had in policy gradient, right? You're trying to maximize sum f under p theta of x. We did all the like fanciness of reinforce. We multiplied and divided and got a grad log and all the other stuff, right? And what that gives you is an objective that looks something like this, right? So you're going to say that if you remember how policy gradient worked, if I had expectation under p theta x of f of x, right? And I'm trying to like get the gradient of it, right? I'm trying to maximize it with gradient descent. When I compute the gradient, I do all the like score matching, multiply, divide by p theta, all the stuff we did in policy gradient, and I just get a grad log in there. So what I'm going to get, if I take the gradient of this objective, is p theta x grad theta log p theta x fx, right? I get this objective, right? remember, I can't take the gradient all the way inside because the expectation depends on p theta. So just the same trick we did policy gradient, right? So the first type of thing, which you'd call the likelihood ratio, the score function, is to say once I have a Q function, I'm just going to like do policy gradient, but I'm going to replace my sum of rewards from my Q function. It's plain, right? So it's going to say, I'm going to sample states from my data set. I'm going to sample actions from my policy. I'm going to increase the likelihood of things according to my Q function. So intuitively, that means that for some state, let's say I sampled some actions, right? And let's say the Q function was like this. I'm going to like increase the likelihood of these actions and like decrease the likelihood of these actions, right? The same thing as policy gradient, but you're just replacing it with Q rather than with sum of rewards. Nothing else, right? So that's the first type of thing we're going to do. The second type of thing, which is used more in practice, is called the reparameterization trick. Have you all heard of this? Anyone heard of reparameterization-ish? So this is the same trick that you use in VAEs. Have you heard of VAEs? Anyone heard of VAEs-ish? Okay, so the idea behind reparameterization is let's say that pi theta was a Gaussian. Okay, so let's say pi theta was a Gaussian. When pi theta is a Gaussian, let's say it had mean mu theta of S, variance sigma theta of S. Okay, and pi theta is a Gaussian, and so this thing is called pi theta. What you can do is you can say, if I sampled an action from here, you can say that this is equivalent to saying an action is equal to mu theta of S plus sigma theta of S times epsilon, where epsilon is sampled from the unit Gaussian. Right? So one way of thinking about it is it's kind of like saying that if I ever want to sample an action from a Gaussian, I can just take the mean and then I can like perturb it by the unit Gaussian scaled by the standard deviation, right? And so whenever I have a Gaussian, this is not true for all probability distributions, but whenever I have a Gaussian, I can kind of separate out the deterministic and the stochastic parts. And now the nice thing is that the stochastic part doesn't depend on theta. The stochastic part is just a unit Gaussian. There's no dependence on theta. And this is a deterministic computation, right? This is completely deterministic. And so what we can do here is we have expectation S, expectation A coming from pi theta, where given S of QSA, right? This is the objective. Now let's write A equal to mu theta plus epsilon theta, sigma theta times epsilon, right? And I'm going to substitute this into here, where epsilon is drawn from the unit Gaussian. Yep. All I've done is I've said, if pi theta was a Gaussian, A is equal to mu theta plus sigma theta times epsilon, right? And epsilon is from the unit Gaussian. And what that allows you to do is it allows you to then say, I can write this as expectation S from D, expectation epsilon from the unit Gaussian of Q of S mu theta plus epsilon theta or sigma theta epsilon. Right? So the nice thing here that I've done is I've removed theta from all the expectations. That's all I've done is I've like, whenever I have this, it doesn't work for all probability distributions, but for a Gaussian, if you can separate out the stochastic and deterministic parts. So if A is equal to mu theta plus sigma theta times epsilon is something that doesn't depend on theta. Then I have this thing where there's no theta in the expectations. And now when I take the gradient of this thing, I just take the gradient all the way inside, right? And so the nice thing about this is that I can just like take the gradient all the way inside. I don't have to do any of this like grad log pi stuff. Right? And so the gradient of this thing looks like S coming from D, epsilon coming from the unit Gaussian. And then you do grad theta of Q S mu theta plus sigma theta times epsilon. Yeah. So what we've done here, we've separated out the deterministic and stochastic parts. The expectation does not depend on theta anymore. So you can take the gradient all the way inside. Okay? And now what you'll do in the last step is you'll use chain rule. So if I have grad theta of this QSA, right, I can write this as grad A QSA times grad A sub theta. Just chain rule. So what I did here is I separate out the deterministic and stochastic parts. These are equivalent. This objective and the objective on top are equivalent. But there's nothing that depends on theta, so I can send the theta all the way inside. Right? And now I've theta all the way inside, and I can use chain rule. Right? And so my objective then becomes exactly what I wrote here. This is just chain rule. This is grad Q SA with respect to A. This is grad A with respect to theta. Right? And so this is what you'd call this algorithm called DDPG, the algorithm called TD3, even SAC. All of them basically use this reparameterization gradient, passes things all the way through, and you don't have to do this like grad log pi stuff. Okay, so what does this mean intuitively, right? Intuitively, imagine this was your Q function, okay? What the left-hand side does is it says, let me sample a bunch of random stuff, and let me increase the likelihood of the good stuff, let me decrease the likelihood of the bad stuff. But it never uses the geometry of the Q function. It just says like good stuff goes up and bad stuff goes down. What the right-hand side does is it like use the gradient of the Q function. So what it does is it says that I'm going to like slide things up according to the gradient of the Q function. So remember, you have a neural net, so you know the gradient of the Q function, right? And so the right-hand side uses the gradient of the Q function to move up and down. So this equation uses the gradient of the Q function. This equation does. And so the way to think about this is the left-hand side is a zeroth order optimizer. You're not taking the gradient of the Q function. The right-hand side is a first order optimizer. You're using the gradient of the Q function. And so whenever you use the gradient, you have more information. The risk is that if your gradient of the Q function is bad, then you're in trouble, right? And so that's the trade-off. Okay, let's pause for 2 minutes and then we'll continue. Oh, we're at 2:06. Should we just finish it? 15 minutes? Or do you prefer a 2-minute break? Break? No? Oh, okay. All right. Great. Okay, then give me 1 second. I'm not able to like delete stuff here. Okay, good. Okay, let's keep going. So as a reminder, let's kind of put all the pieces back together, right? So likelihood ratio is nice because you can apply to any broad policy class. You don't need the like, as long as you have grad log pi, you don't need the gradient of the Q function. The right-hand side is nice because if you have the gradient of the Q function, it tells you which way to go, right? So you can kind of think of this as like shooting darts at a dartboard and hoping that you find it. And you can kind of think of this as like the function tells you which way is going to give you a set, right? And so in practice, this version tends to work better, at least for robots. But there are cases where you can use this one. Okay, so let's put all the pieces together of an actor-critic algorithm. You start by collecting some data. Then you learn a Q function using that Bellman update we had. There's a process called policy evaluation. So what policy evaluation does is it minimizes this objective with respect to Q, right? Or the parameters of Q. And it's going to give you a Q function. Once you have a Q function, you take a step on pi. And then you do the policy again. You do the policy improvement step, right? So this just says, let me find the pi that maximally improves Q, right? And then you go and collect some more data with that new policy. But the nice part about this is that you can just like keep on pooling all your data together. You don't need to like throw away any of your data because this thing can absorb all your data. And this thing, one thing to note here is that you can train it on any state. You don't have to just train it on states under your current policy, right? So both the policy evaluation step and the policy improvement step can be under any data. So you can be off policy, and because you're doing dynamic programming, you can be low variance. Cool. So it satisfies both our qualities, basically AGI. And we can
How
use
far
it
we got financial policy training.
play
You don't see in trial by trial. This is actually every year you trial something.
But
This
this
is
is
really, really
from
trial.
like
The average knowledge trial
18
run
years
for
ago, I
small
think.
like game was around 800 to 1,000 dollars and 500
23
times
years
hit the ball
ago.
on this T-stick
And
until you actually got it.
so,
Pretty good speed.
this particular
Again,
paper is
hard it
actually
is when you
doing
rescue in the robotic, you
natural
have the other one
linear
picking up the ball and
arithmetic, so it's
exactly
doing,
stick.
it's combining some of those ideas we
Again,
had,
reward based
natural
on the
policy gradient
hard
and
hit the ball,
TRPO
who
with
gets the
like,
punishment on this.
it just replaces like this step with like natural policy gradient. That particular paper did that in 2003, and here we are talking about it in 2026.
How far we got them.
Good. All right. That's off policy RL motivation and a first attempt. Any questions before we keep going? Should I recap? Do we feel comfortable? It's a lot of information at once. Yes.
Like, but like, there we can run an application, and we get like the graph from the photograph.
Yes. So it's actually way easier to do it through reprep. So whenever you compute, so here's how you do it with in PyTorch, right? You sample an S from your data set, let's say that. Sample S from a data set. Then you sample an A from like your PyTorch distribution, but just sample it using R sample. When you have PyTorch, PyTorch distributions.R sample, that allows gradients to flow back. And so the way that like PyTorch implements sampling for a Gaussian is by first sampling from a unit Gaussian and then scaling and shifting it, right? And so as long as you do it through R sample, like it'll actually just do it for you. You don't need to do anything else. Like on this side, what you have to do, right? Like to construct this objective, you'd sample S, then you'd sample A, right? Then you'd like find grad log by A, then or actually not grad log, the way that you'd actually construct it is you would sample S, you would sample A, you would get log by A given S, you'd multiply it by Q, and then you would pass that through your torch.backward operation. Right? And in this case, as long as you're sampling A with R sample, and then you stick it into Q, and you pass gradients back through torch backwards, you will already do reparameterization. So super easy. Cool. Yes. Yes. Well, it's all biased. At this point, we're all biased. We're biased all over. But what we'll talk about next, maybe, is the way that this target network, you can kind of think of it as like an exponential moving average of the true target. So you can kind of think of it as like the way you actually do it in practice is that you have like a true target, a true Q function. And this is kind of like a slightly lagging version of that Q function, right? So like this one is like moving, and this one is like a slightly lagging version that like is constantly getting updated by some EMA of the like. So it doesn't move as fast as the Q function. Question. Yes. Yeah, so you are collecting data online, but you're using all of the data in the past. So what policy gradient does is, let's say you had like data at all of these iterations, it like throws away all of this data. Like in this case, what's going to happen is you're going to collect data online, but you're going to, each time you do this update or this update, you use all of that data. Yeah, I think the terminology is a little bit confusing, but I'd say like it's online because you're collecting data online, but it's not on policy because on policy would typically denote you're only using your latest batch of data. So it's like off policy online. That makes sense. But it's just terminology. I think like the main point is you're collecting data online and you're not throwing away these terms. Yeah.
So, like,
Oh, it just works better. Like if you have enough samples, like because we've introduced so much bias into different things, we're approximating things with, like, as I said, this thing is not billion percent. It's like this like fixed point iteration thing. And so the dynamics of PD learning are like much more unstable. So like, for instance, you make the models bigger, it doesn't always convert better. Or like the Q functions sometimes diverge. And so when it works well, it works super well, but it doesn't always work well, especially with bigger models. And so off policy RL is generally a lot more unstable on policy RL. So if I had a lot of samples, I would still use PPO. It just like converges the best. Okay. I think we only have 5 minutes left, so I'm not going to start the next thing, but any questions there?
The pre-parameterization
Yeah.
part said that it kind of relied on us being able to differentiate the policy.
Yeah.
For like some structural pattern. When is that?
So here's an example. When you have a discrete sampling operation. So imagine you were doing a discrete, like your actions were discrete. And so you're sampling A from pi theta is discrete, right? And so in a discrete case, it's like not as easy to separate the deterministic and stochastic parts. Like it's harder to write it as like a sample from something that doesn't depend on theta. And so there's this idea called the Gumbel softmax, which lets you kind of do that, but it's an approximation. And so like discrete is one, you can think of it as like maybe a diffusion policy is another. You can still do it with a diffusion policy in the sense you can think of a diffusion policy as like multiple steps of a Gaussian. If you think of diffusion policy as multiple steps of a Gaussian, then you can like pass gradients back. But because it's multiple steps, it tends to blow up and be unstable. But the easiest example of where it's hard to do is a discrete distribution. So yeah, people tried doing this thing for a diffusion model. It just like tends to work quite poorly. And so what you often do is like something that looks like that.
Why do we not use root parameterization for policy gradient? Is it like if we had a Gaussian
Yeah.
policy, like
Yeah.
is it because our rewards aren't differentiable?
Yeah, so if you knew the dynamics of the world, you could. But the problem is like if I have sum of R, right? Like what you're looking for is sum of R with respect to the gradient of sum of R with respect to A, which means that if I like there's variants of this where if you know the dynamics of the world, you can take gradients through the dynamics. But if I don't know the dynamics, I don't know the gradient of the sum of rewards with respect to the action. Right? And so the Q function in some ways gives you like a surrogate for that gradient, right? But like the sum of rewards does. Good question. Okay, I think let's end it there, but see you on Wednesday. Thanks.